In this video, I'm going to walk you through how to plan and perform a gold standard meta-analysis. This is based on a recent paper, and if you're interested in looking at the specific code underlying this meta-analysis, you should have a look at my other video. Now, let's say we have a research question. Is conscientiousness related to medication adherence? Perhaps people who are more conscientious are more likely to adhere to their medication. Now, one way of looking at this is simply by vote counting. Perhaps we have 8 studies that say yes and 8 studies that say no. But what do we conclude? Now, one way of doing this is by performing a meta-analysis, which is an objective and transparent statistical integration of evidence from multiple studies that address a common research question. In this presentation, I'm going to be going over the gold standard approach to doing a meta-analysis. It may take longer than other approaches, but I'm going to show you that it's worth it. The other thing I really want to drive home is that doing a meta-analysis itself isn't particularly hard. It's just a lot of hard work. There's a number of reasons why you should actually care about doing a meta-analysis. Firstly, they're really useful for grant applications. If you really want to demonstrate the state of the field, a meta-analysis is a great way of doing that. On a larger perspective, they can also be used to direct health policy. It also provides a great framework for a review, and meta-analysis tend to get a lot of citations. The reason being is that meta-analyses solve problems, and in this case, it's what is the state of a particular literature. If your paper can solve a problem, it's going to get a lot of citations and a lot of reads. They're also getting really popular. Here's an analysis I did looking at the number of meta-analyses in the psychological sciences. And when you actually compare it against all articles published overall, there's been a humongous jump, particularly from about 1990 onwards. And a number of journals are also publishing meta-analyses, at least within psychology, but this is relevant to almost every field. Now, like a clinical trial, you should be putting together a protocol for your meta-analysis and also pre-registering your analysis plans. The reason being is that it's easy to game a meta-analysis to get a desired outcome. You have to watch out for this in other papers. As meta-analyses are often used to direct health policy, they should be held to the same standards as clinical trials. Firstly, are they pre-registered? And secondly, are there any conflicts of interest? Here's a great illustration put together by Neuroskeptic, which is the 9 circles of scientific hell, which look at particularly 9 particular problems within the psychological sciences. Now, within meta-analysis, there's a few so-called sins which are often overlooked, which is p-value fishing, which you can do quite easily in meta-analysis unless these things are pre-registered. The same with creative outliers. If your study isn't pre-registered, it's quite easy to look at an outlier and think of a creative way of removing them. So pre-registration helps against this. These are the Prisma P guidelines, which is the preferred reporting items for reporting a systematic review and meta-analysis protocols. And these are really important steps and things that you should include in a protocol for a meta-analysis. So check these out when you're doing your own ones. Now, when you're pre-registering, it improves the confidence in your findings. And it also becomes an important part of your planning process because it really makes you think about what you're going to be doing with your meta-analysis. And it also helps avoid duplication. Perhaps there's another team which is working on the same research question, but if your study is pre-registered, you can actually check these things. Now, one thing that's really important to highlight is that it's okay to change your plans after you've pre-registered your meta-analysis. As long as you're transparent and explaining why your plans changed from what you put in your pre-registration to what you put in your publication, that's fine. It's all about transparency. There are 2 options you can use, or 2 popular options that you can use for pre-registration. Prospero is a website where you can pre-register your protocols, but you can also pre-register on Open Science Framework. Other options include actually publishing your protocol in a journal like Systematic Reviews. By doing this, you're actually going to have your protocol peer-reviewed in an open access journal that anyone can find. But one of the cons to this approach is that it can actually take a few months when you're going through the peer review process and getting the paper actually published online. Another alternative is publishing your protocol at PeerJ preprints. The good thing about this option is that it's instant and it's free, but one of the cons is it's not peer reviewed. However, others can actually comment on your protocol after it's been published. Okay, now we've come to the stage for the literature search and data collection. First thing you need to do is to identify appropriate keywords for your database search. For example, you might use conscientiousness and adhere. Now, we're just going to spend a few moments looking at this thing. Look at the asterisks after adhere. Now, in most databases, with this asterisk, it's going to use any word that contains the first 5 letters there. So adherence or adhere would get covered by that term there. Now, there's a few things to consider when it comes to your search terms. If your search terms are too wide, you're going to waste your time by getting too many hits back, and it's going to take a long time actually going through, and you're going to have a lot of irrelevant papers. If it's too narrow, however, you may miss some papers, so it's important to get these terms right. Now, there are usually 2 databases used, a number of different options. One example is using PubMed and Embase. Now, the important thing is that your search should be reproducible. So when you're reporting your results in your paper, someone can go back, look at the search terms, look at the dates you actually searched them, and find the same results. Now, it's really important to, one thing that can really improve your literature search is talking to your local librarian. They can be an enormous help when it comes to putting together your search terms and the databases that you're going to use. So make sure if you have that resource available that you actually do that. They'll be very happy to help. Once you've found these papers, the next thing you can do is snowball by looking through these reference lists to make sure you haven't actually missed any terms. Another thing you can do is something that I call reverse snowballing. It is which means looking back at who has actually cited your eligible papers in Google Scholar, which is an option that you can do there. Just another way of making sure that no papers are missed. And it's also good to pilot your search terms before you begin. When you're collecting data, it's really helpful to have a data collection form which helps standardize your data collection. Now, this is usually part of your protocol. Here, you'll collect the effect sizes and relevant study information. Usually, 2 people will collect data with a third adjudicator to solve any potential agreements in data collection. Here's an example of a form that I've used in a previous meta-analysis. So here we covered study information, we gave each study an ID, we entered the title, the initials of the reviewer or who was actually completing the form, and we looked at the inclusion criteria, age of participants, sample size, diagnosis, comparison groups, all things that were relevant for the meta-analysis that we were doing. Now, what if data is missing from a paper? This is a common problem. One thing you can do is contact the author. In my experience, about 50% will respond with the data. Now, if it's a paper that's been done a number of years ago, the chances of getting data back are a bit more slim, but it is still worth contacting the author in case they have the data that they can send to you. Now, if there's no response, one option that you can use, which works in some circumstances, is using a plot digitizer. You can actually use this to pull data from figures. In our experience, we've found it's about 99% accurate. So they perform quite well when it comes to actually pulling data from plots which may not be reported in text. The next question is whether to include the grey literature. Now, this is research which isn't formally published, like conference abstracts or dissertations. An advantage of including the grey literature is that it reduces publication bias risk, which is the idea that people are less likely to publish their papers if they didn't get a significant result. But a disadvantage is that quite often these conference abstracts or dissertations can be of poorer quality compared to peer-reviewed papers. One option is actually including the status of whether it's from the grey literature as a moderator. You just need to make sure that you justify your decision. Now it comes to the analysis. You can use SPSS plugins or dedicated meta-analysis software, but both are expensive and it's very hard to reproduce these analyses. One thing which I'm really a big fan of is using R to perform your analysis, as it's free and you can share your script so others can actually reproduce your analysis. So here is an example meta-analysis which includes 16 studies. Going back to our research question, it is conscientiousness related to medication adherence? For this, there were 16 eligible studies that assessed this research question. 8 reported significant correlation and 8 don't. And here's what we do. Now, as I mentioned before, if you actually want to go through step by step for the analysis in R, you should check out my other video or my paper, and you can see the code so you can do this. But I'm going to go over it here anyway. First thing you'll do is import the CSV file, which has all the data. And within this file, it has the Pearson's R correlation, which was reported from each individual study. And you'll convert Pearson's R into Fisher's Z. This is important as Pearson's R isn't normally distributed, but by converting it to Fisher's Z, it is. Then you'll calculate the corresponding sample variances of Fisher's Z. And like with any meta-analysis, you'll be converting all these values to a common effect size. So for instance, you'll be converting P to Cohen's D, or F to Cohen's D, or T to Cohen's D. Or you may convert to Hedges G, which is another common effect size, which is commonly used. So in this example, line 25, we're importing the data set. Line 26, we're adding a study ID column, just from 1 to 16. And line 27, we are adding, moving the study ID column to the front. And the command on line 31, we are viewing the data. This command here converts R to Z, like I mentioned before, important to do because Z is normally distributed. Now, for the meta-analysis models, there are 2 models that we can do. The fixed effects model assumes that all studies are from a single common population, which are tested under similar conditions. So an example of this is a series of experiments which is done in the same lab. Now, the random effects model assumes that studies are drawn from different populations, and this is almost always the case for most meta-analyses. However, even if a random effects model is applied to an homogeneous set of studies, say from the same lab, it will calculate a confidence interval that's equivalent to the fixed effects model. So there's no harm in choosing a random effects model if there's any doubt. For the actual analysis itself, on line 51, that's how you perform it. And then what you'll want to do is you want to transform Fisher's Z back to Pearson's R with confidence intervals, so it's much easier to interpret. And then there's also a command to look at measures of heterogeneity. That is, how different are these studies? Now, the Q statistic is one measure of study heterogeneity, which is a null hypothesis significance test that evaluates the null hypothesis that all studies are examining the same effect. Now, this particular measure is quite sensitive to sample size. However, there's an alternative. The I-squared statistic is a percentage that represents the proportion of observed variation that can be attributed to the actual difference between studies, rather than within study variance. Now, this isn't sensitive to sample size, and there's a few suggested thresholds of 25%, 50%, and 75%. Here's the output here, and within that output, we do get these measures of heterogeneity. We get the Q statistic, which is near the bottom of the green rectangle, and we also get I-squared as well. So this was 61%, so it's somewhere between medium to high variance in this case here. And near the bottom, we have the actual meta-analysis. So the estimate was 0.15 if we're going to be rounding up. Now, what we're going to be doing is next converting Fisher Z back to R, so it's much easier to interpret. And by doing that, our final predictor is that the summary effect size, or the summary Pearson's R, is 0.15. And below that, we have measures of heterogeneity with confidence intervals. Now, heterogeneity is handy because it can tell you that a set of studies are different, but it can't tell you which studies in particular are contributing to this overall heterogeneity. What you can do is a Bauer plot, which can identify studies that excessively contribute to heterogeneity and the overall results. As you can see from this plot here, studies 10 and studies 12 are standing out quite a lot. So it's a nice visualization of what's happening. You can also run diagnostics tests for outliers. Now, within this particular set of tests, there's nothing that particularly stands out. So although we noticed a high degree of heterogeneity, this wasn't driven by one or two particular studies. So there's some reason to believe these studies are standing out, but it doesn't stand out too much. A handy way of visualizing meta-analysis is by using a forest plot, using these commands here. Within this forest plot, studies with larger squares have contributed more to the summary effect size. And the summary effect size you can see down here with the black diamond. There's a dotted line to represent the correlation coefficient of 0, and because the diamond doesn't cross 0, we can see that there is a significant relationship. Now, a big problem within the biomedical sciences is that null studies are never written up. Publication bias is the phenomenon whereby studies with stronger effect sizes are more likely to be published and subsequently included in a meta-analysis. Now, one approach that you can use is constructing a funnel plot to examine potential publication bias in meta-analysis. Within R, using the metaphor package, it just requires one line of code. And here's what we get. Now, there's a line which is centered on the summary effect size, and studies should be equivalently spread on both sides of this line. On the y-axis, we see standard error, and on the x-axis, we see the correlation coefficient. Studies with smaller standard errors are near the top, whereas studies with larger standard errors are near the bottom of the pyramid. Now, we can see here within this sample that it's fairly symmetrical when it comes to studies on both sides of that summary effect size line. Here's an example of an asymmetrical funnel plot. Down the bottom left of the pyramid, there's a lot of missing studies there. There's a big degree of asymmetry in this example. One thing you can do is you can actually impute these missing studies using the trim and fill procedure, which is fairly straightforward to do within R. Now, within R, it actually adds in the imputed studies using these clear circles here. So once you include these clear circles, now this plot looks much more symmetrical. You can see, combining all these three things together, that the trim and fill procedure does a pretty good job at imputing these missing studies. Just compare panel C with panel A. If anything, it slightly overestimates these missing studies. The main thing that the trim and fill procedure should be used for is a form of sensitivity analysis to assess the potential impact of these probable studies on the summary effect size. Quite often, a lot of people use this as a replacement for real studies. So what they do is they find evidence of publication bias or asymmetry, add these studies in, and then report this they include these imputed studies and report that as their main result, which shouldn't be done because these aren't real studies. Funnel plots obviously provide a nice visualization, but they're very subjective. One asymmetrical plot may look symmetrical to someone else. It's all in the eye of the meta-analyst. There are statistical tests for publication bias. First, you can do the rank correlation test, which evaluates if effect size estimates and sampling variances for each study are related. A significant test is consistent with a non-symmetrical funnel plot. There are some issues with using this for small sample sizes, which is around under 25, but there is another option, which is Egger's regression test, which is a better option for smaller samples. Within R, it's one simple command per test. And here's our result. On the top, we have the result for Egger's regression test, and on the bottom, we have the rank correlation test. Now remember, we had evidence of significant study heterogeneity. And what we may find is that moderating variables contribute to this observed variance. So what you can do is a moderator analysis to determine the source or the potential source of this observed heterogeneity. Here's an example of some meta-regressions that we performed in a recent meta-analysis. So for this meta-analysis, we were interested in the impact of average patient age, the percentage of sex, male or female, a measure of study quality, and the year of publication, whether these four moderators had an effect on our overall meta-analysis. So we found that there was evidence of year of publication. So for instance, there were actually smaller effect sizes for more recent studies. This is looking at panel D, by the way. There were smaller effect sizes for more recent studies, whereas studies that were performed a number of years ago tended to have slightly larger effect sizes. And we found something similar when it came to study quality. This is looking at panel C, in that studies that had higher study quality tended to report larger effect sizes. So this is one example or one way that moderator analyses can be used. In this example, I'm going to go into what the impact of age is on the overall effect sizes. Now you use a very similar script as with the typical meta-analysis, just with the addition of the age moderator. In this example, it wasn't statistically significant. The other thing is asking the question what the impact of having controlled variables on the overall effect size is. Once again, we use the same script, except we add the controls moderator. And in this example, we found that this was statistically significant. Now, you tend to find that some studies report multiple effect sizes. This can be an issue because if you're including these multiple effect sizes from one study, there can be issues of dependency. So you need to find ways of actually accounting for this. In this example, we have 3 effect sizes from one study. Now what you can do is, you can actually fit a meta-regression model with the correction for small sample size. And here we found a statistically significant effect. Now it's really important that you follow the PRISMA guidelines for reporting your meta-analysis, so make sure you look that up. By doing this, it actually helps, for one, it's the gold standard, but for two, it helps standardize the reporting of meta-analysis. If you're interested in reading more about meta-analysis, here are 2 books that I recommend. Understanding the New Statistics, which is a more recent book, and An Introduction to Meta-Analysis, which goes through a lot more of the theory there. Thanks for listening. If you do have any questions, just leave a comment, or you can contact me on Twitter @DSQuintana.